Hello everyone, welcome to this session. So in the last session, we have discussed the hard margin classifier. In this session, we will introduce the soft margin classifier. So in this session, we will introduce some mathematics, but the goal is to let you understand how the soft margin classifier works. The mathematics themselves are mostly not required in this specialization. Okay, now let's start the soft margin classifier now. As we have said, in real-world data, most of them are not linearly separable, right? So one kind is there are outliers. So as we can see here, for this data, if we use a hyperplane, to divide them into two classes, there are outliers here, right? Although this is not linearly separable, it's nearly linearly separable. And except there are outliers, and the goal is to handle them. So how to handle them? The method is a soft margin SVM. So soft margin SVM, the key thing is that we allow misclassifications considering these outliers, but we don't want them to be many, so a penalty is given. Then we need to consider the trade-off between the maximizing the margin and minimizing the number of misclassifications. So how this trade-off goes, so we will describe it in the later slide. First, we need to understand the support vectors when we consider this non-separable case is different from the separable case. So if we considering the linearly separable, we can recall the support vectors, there's only one type, and they are those that lie on the margin boundaries. So if we see this figure, we have class positive 1, class negative 1, and this is a hyperplane, and we have two margins. So where are the support vectors? So these are those that lie on the margin boundaries, right? But in soft margin, this is different. We have three types of support vectors. The first type, let's say class positive 1, class minus 1, they're still hyperplane with two margin boundaries. The class 1, this is the same as before, lying on the margin boundaries. This is the same as the hard margin cases. The type 2 we can see is like this. So they lie between the margin boundaries, but they still on the correct side. So for example, this one, if we considering this is the margin boundary of the class positive 1, this one lie on the wrong side of the margin boundaries, right? But it's still on the correct side. We can see this point is like this. This is the same, right? So we call this is another type, the type 2 of the support vectors. And there's another type 3. So these just lie on the wrong side of the hyperplane, like this point and this point. So they are on the wrong side, right? Not in the correct class. So we have three types of support vectors. In soft margin classifier, we use a slack variable zeta. The goal is to allow for margin boundary violation and even misclassification in the optimization problem that is solved in the SVM optimization. So we can see here is a class positive 1, class negative 1, hyperplane, the decision boundaries. And for the three types of support vectors, we can see the type 2. We can see is here and here. They violate the margin boundary, but they are still not misclassified in the correct side. And so the type 3 points, they are already misclassified. And we need to allow them to some extent. So in this way, we need to do some change, right, to the original problem that we used in the hard margin classifier. So we can see it here, right? So what's the new problem? We change it like this. So we can see the zeta is here. These are the slack variable vector to relax the condition of the hard margin classifier. And we add it here. So why we do it like this? So we can see it like this. First, the slack variable, what is the goal? This one indicates that how much the points can violate the margin. So we can see it's here, relaxed condition, and we add it here. So we can see the goal is that we want the violation of the margins to be minimized, although this is allowed, right? So because of this, we minimize the sum of the slack variables. So we can see this is here, right? To minimize the sum of them. So we call this term the penalty for margin violation. So we can see there is a variable c. This is a constant here, c. So this c, this is a hyperparameter with the goal is to control the trade-off between this term and this term. So this is to trade off between the margin violation allowed and the margin themselves. So if the value of c is large, this means a small violation can cause a large increase of the objective function, right? So in this way, we prefer a small margin violation. So otherwise, when the c is small, this term becomes more important. So we prefer the large margins. So this is the trade-off. So for more details, you can look at this hyperlink. So this is optional for this specialization and not required. Then, when we know the optimization problem we want to solve, then we need to see how we solve it. So we can see this problem we just listed, we call this primal problem. So we can see in this problem, we optimize the decision variables are the W, B, and theta. So there are 2n plus 1 of them. So considering the number of design variables is a bit larger, so this problem is a bit difficult to solve. To make it easier, we often solve with a dual problem. The dual problem is equivalent to this. So we can see this is a problem here. So in this problem, we only optimize the alpha. So alpha is a variable of the n dimensions, right? N dimensions. So it's easier to optimize. So normally this is optimized instead of this one, right? So when you see why these two problems are equivalent, I also provide a hyperlink for you, and you can see this. So in this dual problem that we want to solve later, we can find this one. So this one we call it a dot product. So we need to understand what it is because we will use it in the coming sessions, right? So dot product is mathematical operations between two vectors, and the result is a scalar, right? So this is how it goes. Consider xi and xj are two vectors of d dimensions. The dot products xi dot product xj, this is equivalent to xi with the transpose and multiply xj. So it means that we element by element multiplication, then we sum them together. So for this equation, we can know this is x1i multiply x1j plus x2i multiply x2j until the end. So we can see, we write it in a mathematical way, it's like this. So let's give you an example. If 2, 3 dot product 4, 1, then we use these two, we multiply them, and the other two multiply them, then we sum them together, then we will get the result, right? Now we will solve the dual problem for this one. Yeah, so here we can see this is a dot product. And we can see here, there's also, besides this constraint, the alpha I, yi, we sum them together, this is 0. There's another constraint. We have the range of the alpha I, the decision variable, from 0 to c, right? So this is a search range, as we have learned before. So here we call it the box constraint. So box constraint confine the design variables within a certain range. So for example, if we say there are alpha 1 and alpha 2, both of them from 0 to c, then the feasible region is this box, right? So now we know this dual problem. By optimizing this dual problem, we get the optimal value of alpha I, then the soft margin classifier is trained, right? Then it can be used for prediction. So in the last slides, we will use the iris flower case, as we have seen in the last session, and we use two C. One is smaller, one is larger. to see the trade-off between the margin itself and the margin violation. So first one, the C is small, and we can see that this allows for more support vectors, right? And the margin violation is larger. In contrast, if we use a large value of C, we can see here, then we can see the margin is itself is smaller, but the margin violation is also smaller, right? So we can see this one, we have a more generality, and this one, we have a more strict classification. So when the value of C becomes infinity, so here is the question, what will a soft margin classifier becomes? So consider C is infinity, so this means the penalty term becomes infinitively large, right? So then, in this case, the soft margin classifier becomes the hard margin classifier. So no margin violation is allowed. Okay, so this is the soft margin classifier introduction. So what you don't need to understand all the mathematics in it, but you need to understand how it works and this trade-off, right? Okay, thank you very much. Bye-bye.